Morning, students. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today, in this session, I want to explain what is the effect of loading on endurance limit. In previous sessions, already we have learned fatigue failure and endurance limit. So in this session, what is the main effect of loading different whenever the object is subjected to different loading? So what is the effect of endurance limit? How to calculate this endurance limit for different loading? We will see. So the effect of loading and endurance limit, the load factor we have to take. So how many loads are there and how to take this load factor I will explain in this session. Actually, the standard specimen is subjected to reversal bending loads. So whatever we have tested, the standard specimen under a fatigue test, so we have plotted those values on SN curve. So by using that diagram, we will find fatigue strength of an object for a particular number of cycles. Sometimes the whole mechanical members also subjected to other than these reversal bending loads. Maybe it may be subjected to axial loads. It may be subjected to shear loads. So in that case, the endurance limit value you have to calculate by taking the load correction factor for the particular corresponding loads. So the endurance limit of a material as determined by the rotating beam method, so that is the fatigue testing method, is for reversal bending load. Same endurance limit, we will take that depending upon the type of loading. So that endurance limit we will multiply with these other load factors. Let example take KB here, load correction factor for the reversed or rotating bending load. So its value is usually taken as unity. So always you should take the KB is equal to 1. And the load correction factor for the reverse axial loads. Suppose the member is subjected to reverse axial loads. In that condition, you should take the Ka value, reverse axial load factor. It may be taken as 0.8. So Ka is 0.8. So sometimes they may not given in the problem. So in that time, you have to assume the Ka value is 0.8. Suppose if you don't know all correction factors values, so you may assume 1 also. So other loading factor is shear loading factor. The load correction factor for the reversed torsional or shear load. So whenever the mechanical component is subjected to shear load, you should take the shear loading correction factor for calculating the endurance limit. So it means this value, the Ks or Kb or Ka values, you should multiply with sigma E. So then only you will get the endurance limit for the particular material. So endurance limit for reversal bending load, here shown, Ke sigma Eb is equal to sigma E to Kb is equal to sigma E. So load correction factor for shear loads may be taken as 0.55 for ductile materials and 0.8 for brittle materials. So suppose if you selected material is ductile material, so you may assume 0.55 for ductile and 0.8 for brittle, that is Ks value. KS 0.8 for Britain and Decton. So now calculate the endurance limit for different loading one by one. First you take reversed bending load. In reversed bending load, the new endurance limit for reversal bending load is equal to sigma E. So whatever you determine under rotating beam testing method, sigma E value substitute here and KB. So KB is always you may take a KB is equal to 1. So that sigma EB is equal to sigma E into 1 sigma E. You can say the endurance limit under a reversed bending load, same as endurance limit for a standard specimen. So endurance limit, whatever value determined from by using rotating beam fatigue tester. So that those value you can substitute in this, you will get endurance limit for a desired material. Similarly, you may calculate another endurance limit for reversed axial loads. Suppose your component is subjected to reversed axial loads, sigma EA. So find out sigma EA is equal to sigma E into K. So in this also, the K value you may assume, you may take, so here 0.8 as we discussed in previous slide. So that 0.8 sigma E. This is under reversed axial load. Similarly, the third one is endurance limit for reversed torsional shear loads. Whenever the object component is subjected to shear load, shear stress, shear endurance limit is equal to sigma E multiplied with Ks. So shear load factor, here you may take 0.55 for ductile materials and 0.8 for brittle materials. Suppose if the material is ductile material, sigma E 0.55. So 0.55 sigma E for ductile material. For brittle material, substitute value sigma E multiply with 0.8. 0.8 sigma E. Same as axial load correction factor, Ka. So like this, you need to calculate endurance limit values for different loads. So the endurance limit value is depends upon the type of load. So that's why it may vary from load to load, and also depends upon the material. So other correction factors also there. So effect on this endurance limit, I will discuss in next slide. So now the effect of surface finish on endurance limit. So that factor is called surface finish factor. So you can take the surface finish factor, you may use K surf. So this value, this surface, this endurance limit depends upon this the surface of the object. So suppose your object is mirror polish. So suppose your object is very surface finish is very poor. So the endurance limit may vary. It may be increase or decrease, depends upon this surface finish condition. So that while calculating problems, while solving the design problems, you may assume the surface finish factor also. If not given in our problem, you should take the surface finish factor is 1. So again calculate endurance limit for reversal bending load, reversal axial load and shear load. So now we will see. First to calculate endurance limit for reversal bending load. The first one, sigma E for reversed bending load. Since reversed bending loads, so already we calculate sigma EB is equal to sigma E multiplied with KB. Now, while considering, whenever you are considering the surface finish factor, again calculate the new endurance limit. So that is sigma E1 sigma EB multiply with K surface finish factor. So now substitute this K sigma EB, sigma E into KB into K surface finish factor. This is our endurance limit value for reversed bending loads while considering surface finish factor. So considering surface finish factor, then you will get endurance limit for a particular object is sigma E into KB into K surface. Similarly, for reversed axial load, so in a reversed axial load, sigma E, whenever the loads are for second one for reversed axial loads, sigma EA, sigma E multiply with KA. So now, while considering surface finish factor, sigma E1, sigma EA multiply with K surface finish factor. So sigma EA is sigma E into KA, K surface finish factor. So this is for endurance limit. So you should multiply whatever given the factors, the load correction factors with sigma E value. Similarly, third one, for shear loads, tau E1 is equal to tau E multiply with K shear factor plus K surface finish factor. Clear? So like this, how to calculate endurance limit values for different loads when considering surface finish factor. So one more factor is there. So that is size factor. Effect of size on endurance limit. So that is size factor K size. The endurance limit value depends upon this component size. Suppose your specimen dimensions are very large. So the larger specimens always will have more defects, so that the endurance limit value may be decreased. So less value the endurance limit will get. If the size of the component is exactly for standard specimens, standard dimensions, so you will get good endurance limit. Suppose if dimensions are vary, so the endurance limit value also different. So that's why you should multiply, you should take the size factor into account for calculating endurance limit. While solving problems, we need to multiply size factor also. suppose if they are given in your problem size factor, so same value you need to substitute. So otherwise you may assume 1. So again calculate when considering size factor. So what are the endurance limit values for different loads? So again calculate first one for bending loads, for reversed bending loads. So already we have calculated sigma EB is equal to sigma E KB. And also you have calculated with considering surface finish factor sigma E KB multiply with K surface. Now you are taking size factor also, so that's why sigma E dash, that is sigma E1 multiply with K size factor. Again we'll get a new value endurance limit. You can write sigma E in the sigma E dash. So sigma E1 multiply with K size factor. So it means sigma E into KB into K surface finish factor multiply with K size factor. This is our new endurance limit value. Similarly for axial loads. Axial loads, considering this size factor. So take axial loads. For axial loads, sigma EA, already you know sigma E multiply with KA and sigma E1 is equal to sigma A KA K surface finish factor, sigma E dash new one. Now considering size factor, so KA K surface multiply with K size factor. Yeah. So similarly for shear loads. Shear load, third one, for shear loads, tau E is equal to shear loads tau E into K Ks shear factor multiply with Ks and K surface finish factor K tau E1. So E dash tau E Ks K surface finish factor multiply with K size factor. So now obtain a new endurance limit and considering size factor, surface finish factor and loading factor, shear loading factor. So now other than these factors, the miscellaneous factors also there. So what are they? Effect of miscellaneous factors on endurance limit. Other factors also will affect. So those are the other factors are reliability factor. So KR. Impact factor, impact loading factor, KI. And temperature factor, KT. So this is reliability and then impact, and this one is temperature. So while considering all these factors, in addition to the previous factors, need to multiply these factors also. And one more important factor also there, that is fatigue stress concentration factor. that is Kf. Fatigue testing, fatigue stress concentration factor. Fatigue stress concentration factor, they will give in problem. Otherwise, you may assume 1. So otherwise, sometimes you may calculate you get this value by using notch sensitivity factor or theoretical stress concentration factor. So relation also there. So already we have studied in earlier sessions. So Kf minus 1 by Kt minus 1 notch sensitivity, that is Q, is equal to Kf minus 1 by Kt minus 1. So you may write here Kf minus 1 is equal to Q into Kt minus 1. So that you may write here Kf value, fatigue stress concentration factor is Q multiply with Kt minus 1, Kt theoretical stress concentration factor plus 1. If you know the value of mass sensitivity and the theoretical stress concentration, you can calculate Kf. Otherwise, you may assume 1 value. So this one also other miscellaneous factor. And reliability factor, already I told you, temperature and impact. Suppose we are considering all these factors. So how do you calculate the endurance limit value for reversed bending load? Again, you take 1 by 1. So here, first load for bending load, sigma EB is equal to sigma E into KB. And considering surface factor, K surf, size factor, sigma E KB, K surface finish multiply with K size factor. Considering reliability factor and then impact factor, fatigue testing factor, other value E dash or otherwise sigma E2 is equal to sigma E KB, K surface finish factor, K size factor multiply with K reliability factor, K fatigue stress concentration factor and K impact factor multiply with KT temperature factor. Whatever values available given, the all factors you should multiply with the endurance limit value. Then you will get the actual endurance limit of a particular material. Similarly, for axial loads, axial load, second one, sigma E2 is equal to sigma E, Ka, K surface, K size factor multiply with Kf or Kt, etc. Similarly, for shear loads, shear endurance limit, K shear factor, here K shear correction factor, K surface, K size and Kf into Kt. So like this, need to multiply the given factors with the endurance limit. So you can calculate the actual endurance limit. So that up to now we have learned what is the effect of endurance limit on different loading and how to calculate also. You have learned this one completed. Next. So what is the relation between the endurance limit and ultimate tensile strength? These relations are very useful for problem solving. So it has been found experimentally the endurance limit of a material when subjected to fatigue loading. So what is fatigue loading? Already you know the fatigue failure. So whenever the component is subjected to cyclic loads or repeated loads, the component will fail below the yield point after number of cycles. So this phenomenon is known as fatigue failure. So here the fatigue loading is a function of ultimate tensile strength. So that for steel material, the sigma E 0.5 times of sigma U. So that is half of the ultimate strength. So similarly for casting, 0.4 sigma U. Say for cast iron, 0.35. And for non-ferrous metals and alloys, 0.3 sigma U. So here, to take these relations between the sigma E and ultimate tensile strength. Just a factor of safety for fatigue loading. So what is the factor of safety for fatigue loading? The factor of safety is equal to, it is the ratio of ultimate stress to design stress or working stress. The normal factor of safety already you know. So why should you take a factor of safety? To avoid failures, always for safe design. So for fatigue loading, so whenever the component is subjected to cyclic loads or fatigue loads, in that you should take the endurance limit stress upon here design stress or working stress. So that, so you may write here like this: factor of safety for fatigue loading is equal to sigma E divided by sigma T. So this is factor of safety for fatigue loading, endurance limit to the design stress or working stress. So now we will see one problem on this. Determine the design stress. In this, he has asked design stress, that is working stress, for a piston rod where the load is completely reversible. So the type of load is reversal load. The surface of the rod is ground and the surface finish factor is 0.9. The surface of the rod is ground and the surface finish factor K sub given 0.9. There is no stress concentration. So clearly mentioned here, there is no stress concentration. The load is predictable and the factor of safety is 2. So factor of safety also given 2. What he has asked? Design stress for completely reversible load. So for completely reversible loads, the mean stress is 0. So you may calculate other stresses. What are the other stresses? Endurance limit stress. So how to solve this problem? So now we will see. So determine the design stress for piston rod. Here given data. Write down type of load, reversal stress, reversal load, and surface finish factor K sub 0.9, no stress concentration, the load predictable, and the factor of safety is 2. So as for factor of safety of fatigue loading, factor of safety is equal to endurance limit upon design stress. So here the endurance limit is equal to factor of safety multiplied with sigma T. But he has asked design stress. So sigma D is equal to sigma E by factor of safety. So that In next step, sigma D is equal to sigma E by factor of safety. Sigma E, you don't know, factor of safety is 2. But you may assume, already I told you in previous slides, for steel material, sigma E is sigma E is equal to 0.5 times of sigma U. For cast steel, 0.4 into sigma U. For cast iron, 0.35 sigma U. For ferrous metals and alloys, 0.3. So you may assume one material. Suppose you assumed the steel material or cast steel material for piston, so sigma E. So material is here piston rod component is. So you may assume this cast steel 0.4 sigma U by 2. This is our design stress in terms of ultimate strength. So like this, you have to calculate. Next one is combined steady and variable stresses. So here, whenever the component is subjected to variable loading, variable stresses, you can't use the empirical relations. You can't solve by using preliminary equations. Need to use some specific methods. Those methods are derived by using these combined steady and variable stress experiments. The failure points from fatigue tests made with different steels and the combinations of mean and variable stresses are plotted. So I will show you the diagram. So as a function of variable stress and mean stress. So here in x-axis take mean stress and here variable stresses. Here ultimate stress and sigma y you may assume. Here in this the ultimate stress, variable stress, here you may take endurance strength. By using this diagram, so mean versus variable versus mean, different methods developed. Those one is Soderberg line method, Gerber parabola, another one is Goodman line theory. So these three methods are there for calculating the variable stresses and mean stresses whenever the component is subjected to combined steady loads. So this is the diagram. Here variable stress on y-axis and mean stress shown on x-axis. So right side is tensile and left side positive, compressed to negative. So these all points are failure points. So this line is Soderberg line. This Soderberg scientist derived this equation for calculating the variable stresses. The line drawn between the sigma E endurance limit to yield strength. Similarly, ultimate stress to sigma E. Goodman line method. If you have drawn the parabola, the curve from sigma E to sigma U, so that is ultimate strength. This parabola is called a Gerber parabola. So three methods are derived. One by one, I will explain the equation formula for these variable stresses. So by these empirical relations are very useful for problem solving. So first you take Gerber method for combination of stresses. So first you Gerber method. So here x-axis and y, take the maximum endurance limit, the maximum stress, variable stresses, and mean stresses. Sigma U ultimate strength to sigma E. So this is a parabola Gerber method, Gerber parabola, as shown in a previous diagram. So all these here failure points up to this zone, the component will not fail. So behind these values, the component may be fail. So by using this method, one equation is derived for calculating the design parameters of a mechanical component. 1 by factor of safety is equal to mean stress upon ultimate stress whole square multiply with factor of safety plus sigma V by sigma V. Variable stress by sigma E. Endurance limit value. So first in this, by using this method, you need to calculate mean stresses. How do you calculate the mean stress? So sigma max plus sigma mean by 2. Similarly, variable stress, sigma max minus sigma minimum by 2. So ultimate stress they will give in problem. Sigma E you may calculate. Suppose available sigma U value, you may calculate sigma E based on the relations between endurance limit and ultimate strength. That is depends upon the material. So after that, after calculation of these mean stress and variable stress, substitute in this Gerber method. You will get desired values. So here clearly mentioned factor of safety. Sigma M is mean stress. It may be tensile or compressive. Sigma U ultimate stress, tensile or compressive. Sigma E endurance limit for reversible loading. Considering the fatigue stress concentration factor. Suppose you are considering the fatigue stress concentration factor, the equation may be written like this. Sigma M by mean, there is no change here. Sigma mean stress upon by sigma U whole square plus factor multiply with factor of safety plus variable stress multiply with fatigue stress concentration factor. So already we have discussed it in previous slides upon sigma E. Only you are considering fatigue stress concentration factor. That factor you should multiply with sigma V, variable stress. Goodman method. Next, second one for combination of stresses. So Goodman is a straight line drawn from sigma E to sigma U. Sigma mean here and sigma variable. So this line is called as Goodman. Goodman scientist derived. So according to this theory, Goodman, the 1 by factor of safety is equal to mean stress upon ultimate plus variable stress by sigma E. So this method is useful for brittle materials. The Gerber parabola you may use for ductile or the brittle. So whenever the ultimate stress value is given in a problem, so that is in that case the Goodman method is useful or applicable. In your problem, yield stress is available, so that is Soderberg line method is useful. So I will explain in next slide. Considering the fatigue stress concentration factor. Here also suppose you are considering fatigue stress concentration factor, KF. The equation may be written like this. 1 by factor of safety is equal to sigma m by sigma u plus variable stress multiply with Kf upon sigma e. Considering the load factor, surface finish factor and size factor, the equation may be written in another way. Suppose you are considering load factor, surface finish factor, size factor, whatever you learn in endurance limit topic, already we have studied about these factors. Suppose only you are considering fatigue stress concentration factor, so then you should multiply with sigma. Considering other factors, you may write like this: factor of safety is equal to sigma m by sigma u plus sigma v kf by sigma e multiply with k surface finish factor multiply with size factor. These factors you should multiply with sigma e. Clear? So third method is Soderberg line method. This one also straight line method. A line drawn between sigma e and sigma y. Yield stress. Their variable stresses and mean stress. Soderberg method or Soderberg line. Soderberg line method. The Soderberg method is applicable for ductile materials. So whenever you are ductile material, your component is ductile material, subjected to combined steady loads, then I need to apply this Soderberg line method. So up to here in this zone only, this is a safe zone. Beyond this line, the component may be failure points. So 1 by factor of safety is equal to sigma m mean stress upon yield stress plus variable stress upon sigma e. Endurance strength value, stress value. So in this case also, if you are considering a fatigue stress concentration factor, then you may be written like this: 1 by factor of safety is equal to mean stress upon yield stress plus sigma v into k by sigma e. Mean stress and yield stress, variable stress, fatigue stress concentration factor, and endurance limit. Considering other factors also, size factor, surface finish factor, or temperature factor. So then you need to multiply with sigma e. Considering other factors. Other factors like surface finish factor, size factor, temperature factor, etc. This case, here multiply case of surface finish factor multiply with size factor multiply with temperature factor, etc. Whatever factors given in the problem, you should multiply all factors with sigma e. While considering these factors in addition to the fatigue stress concentration factor. So like this, need to apply these methods for variable load stresses. So now, once again, we will see the total diagram, the combination of all these methods here shown. Gerber parabola is drawn between sigma e, the curve drawn between sigma e and sigma u. Soderberg line drawn between yield stress and endurance limit stress. Goodman line method, ultimate stress between ultimate stress and sigma e. So remaining points are all failure points. The safe zone up to here. Next, now we will see problem solving on these variable stresses. Determine the thickness of a 120 mm wide uniform plate for safe continuous operation if the plate is to be subjected to a tensile load. The thickness given 120 mm, determine the thickness. Need to calculate the thickness of a plate. So the wide dimensions given 120 and type of load is a tensile load and the maximum value is 250 kilonewtons. The minimum value 100 kilonewtons. So it may be vary load minimum to maximum 100 to 250. The properties of the plate materials are as follows. The endurance limit stress is 225 megapascal and the yield point stress 300 megapascal. So the factor of safety based on yield point may be taken as 1.5. So the given data like this, first of all, write down the given data, width 120 mm, the maximum load is 250 kilonewtons, minimum load is 100 kilonewtons, and the sigma E is 225 megapascal. This is 225 Newton per mm square. Sigma Y is 300 megapascal. Yield stress. So you can convert into Newton per mm square. 1 megapascal is equal to 1 Newton per mm square. Factor of safety is 1.5. So now let take small t, thickness of the plate. So calculate area. Area of the plate is width multiply with thickness. We don't know the thickness, you need to calculate. So width already given 120. So that area is equal to 120 times of t mm square. Next calculate mean stresses. So mean stress is equal to mean load upon area. Area already you have calculated. So mean load, how do you calculate mean load? Mean load is equal to W max plus W minimum by 2. Maximum load plus minimum load upon 2. So in this, in our problem, the maximum load is given 250 kilonewtons and 100 this one, so that W mean load 250 plus 100 by 2, 350 by 2, 175 kilonewton mean load. So now 175 kilonewtons convert into newtons and calculate mean stress. The mean stress in terms of thickness we will get. Similarly, calculate variable load. So variable load is W max minus W minimum upon 2. W max minus W minimum by 2, 250 minus 100 by 2. So 75 kilonewton. Now calculate variable stress. Variable sigma V is equal to WV by area. So variable load upon area. So now you have calculated mean stress, variable and variable stress, variable load and variable stress. Now apply suitable method what you have discussed in previous slides. So here Soderberg formula is applicable. So why? Because in our problem sigma E is available and sigma Y. So that is yield stress. So here subjected to tensile load and as a maximum value and a minimum value given, and the yield point stress is given. So that this material is ductile material and the useful method is Soderberg formula. Now Soderberg formula, calculate, we apply 1 by factor of safety is equal to mean stress upon yield stress plus sigma V by sigma E. So variable stress upon sigma E. Here not given any factors. You are not considering any fatigue stress concentration factor and endurance other stress factors. So that substitute the factor of safety values given 1.5, mean stress already calculated in terms of T. The mean stress is in terms of T, 175 upon 120 T into 300. Similarly, sigma V variable stress. So finally, you will get T is equal to 11.46. You can say 11.5 mm. The T, final T is equal to 11.5 mm. So like this, how to calculate the combined study and variable stresses for problems. So one more problem we will see. Determine the diameter of a circular rod. Here given component is circular cross section. In previous case, given rectangular plate, but in this given cross section is circular, made of ductile material also given, with a fatigue strength, the complete stress reversal. So reversal load sigma E 265 megapascal and a tensile yield strength given 350 megapascal. The member is subjected to varying axial load from minimum to maximum. So the member is subject to varying axial load. So here reversal axial load given minus 310 kilonewton to 700 kilonewton. And as a stress concentration factor is 1.8. So use factor of safety is 2. value factor safety given. Now write down the given data. Sigma E 265 megapascal. Sigma E 265 megapascal. Convert into Newton per mm square. And yield stress value 350 megapascal. 350 Newton per mm square. Minimum load minus 300 into 10 cube newtons. Maximum load 700 into 10 cube newtons. Here other factors given here: fatigue stress concentration factor and factor of safety. Here fatigue stress concentration factor given stress concentration factor 1.8. So that you need to multiply these factors while I'm writing formula. In that case, in that formula, you should multiply Kf and other factors if any. So first to find out the diameter of the circular rod. The circular rod area 5/4 into d square. D we need to calculate. We don't know, unknown. So area will get in terms of D. So now calculate mean load and mean stress. Similarly, variable load and variable stress. The mean or average load here calculated W max plus minimum on 2. So that substitute the given maximum load 700 newtons minus 300 here given minus load minimum load. Mean stress you may calculate load upon area. Clear? So you will get in terms of D. Similarly calculate variable load. Variable load is equal to W max minus W minimum by 2. Variable stress is equal to variable load upon area. So know that according to Soderberg formula, what is the Soderberg formula? 1 by factor of safety is equal to mean stress upon sigma y plus variable stress upon sigma e without considering any factors. So now here given fatigue stress concentration factor, so that multiply with Kf. Multiply with Kf value. So now calculate D value, substitute the all above values, factor of safety 2, substitute, yield stress given 350 and sigma mean stress calculated in the previous step. Mean stress is equal to 254.6 into 10 cube by d square plus sigma v variable stress into fatigue stress concentration factor 1.8, so that finally you will get 100.5 mm diameter. And one more problem you will do. A circular bar of 500 mm length is supported freely at its two ends. The circular rod 500 mm length is supported freely at two ends. It is acted upon by a center concentrated load, cyclic load, having a minimum value of 20 kilonewtons and a maximum value of 50 kilonewtons. The center load acting here, this one is free end, freely supported at two ends, and the center load may vary 20 to 50. circular rod. So diameter, determine the diameter. Diameter you have to calculate. Taking a factor of safety is 1.5. Size factor 0.85. Surface finish factor 0.9. So the materials of the material properties of the bar is given ultimate strength and yield strength, and endurance strength also given. Yield strength or ultimate strength and endurance strength also given. So here you need to apply Soderberg line method and then Goodman line method. So first you apply these two methods and find out the diameter. So take the larger value of the calculated values. So first one, given data. The given data, write down the length is 500 mm. The length of the bar is 500 mm. And the freely supported here. There is no fix. And W minimum load 20. Maximum is 50. Factor of safety is 1.5. Size factor 0.85. Surface finish factor 0.9. The ultimate strength and yield strength values are given in megapascal. Convert into Newton per mm square. 1 megapascal is equal to 1 Newton per mm square. So now let D diameter of the bar in mm, and you know that the maximum bending moment value is W max into L by 4, considered as a simply supported beam, so that calculate bending moment WL by 4, substitute maximum value, and similarly calculate the minimum bending moment, and then calculate mean or average bending moment. The average bending moment or mean on bending moment maximum plus bending moment minimum by 2. Similarly, variable bending moment max minus minimum bending moment upon 2. So here you have calculated values, the mean average bending moment and variable bending moment. Now calculate section modulus of the bar Z value for bending stress calculation. Section modulus is equal to Z is equal to pi by 32 into d cube. Here calculated, and now substitute in this equation. Bending stress is equal to mean or bending stress is equal to bending moment upon I by Y. So here I by Y nothing but Z, section modulus. So modulus we are moment of inertia to the distance of the cross section from its neutral axis. Now substitute the calculated mean bending moment. What is the mean bending moment? 4375 into 10 cube. And calculate bending stress in terms of D. Similarly, variable bending stress in terms of D. Variable bending moment upon Z. Now apply Goodman theory. So according to Goodman theory, one-way factor of safety is equal to mean stress upon ultimate stress plus variable stress upon sigma e. This is for Goodman line method without considering any factors. Suppose you are considering fatigue stress concentration factor, surface finish factor, and size factor. Here in this problem given all these factors, so that we need to apply the factors values, and you may be written the equation like this: 1 by factor of safety is equal to mean stress upon ultimate stress plus sigma v into k of fatigue stress concentration factor by sigma e into k surface finish factor and size factor. So here mean stress calculated, mean bending stress by using mean bending moment. Similarly, the variable stress calculated by using variable bending moment. Sigma u available in your problem, and sigma e also given. All factors available. So now substitute those values in this equation and find the d. Similarly, apply a Soderberg line method. So first you calculate this one, substitute sigma m and sigma u value, and sigma v is variable stress is equal to 19.1 to 10 to the power of 6, kf is 1, and k surface finish factor and this size factor you take 0.85 and 0.9 respectively. So finally, you will get the d value 59.3 according to Goodman formula. So apply Soderberg formula. So according to Soderberg formula, so once again write down this formula: 1 by factor of safety plus sigma m by sigma y plus sigma v by sigma e, and multiply with given factors. So once again calculate d by using this Soderberg line method. 1 by factor of safety, sigma mean and sigma y value given 500, and similarly here variable stress given 19.1 into 10 say 10 to the power 6 into 1, and say surface finish factor and size factor. So substitute all values whatever you calculated in the previous step and find out d here. So d is 62.1. In previous calculated d is diameter according to Goodman's formula. According to Goodman formula, the d value is 59.3. So according to Soderberg formula, d is 62.1. So now find a larger value of the above two calculated values. So take larger one, fix as a final diameter. So here taking larger of the two values, you have this one is the larger value 62.1. So this value you can fix as a final diameter of the given circular rod. So like this, how to solve the problems of combined stresses and variable, combined loads and combined steady loads and variable stresses by using this Soderberg line method, Gerber parabola, and then Goodman line method. So I have taken references Bandari, V. Bandari, Raskurmi, and then North. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.